All right. So, good morning again. So, lecture 10, where we start talking about quantum information theory officially and quantum computation. So, introduction to quantum computations and the mathematics of qubits. This we'll cover in lecture 11 most likely. So, as discussed in the class, there is one question posed by Michael Nielsen himself. If we were to contact aliens, how likely are they to have discovered computers? Computers. And of course, we also asked, how about Coca-Cola? And we back and forth debated. We were also interested how likely they are to have calculated the value of pi or similar concepts. Well, the bottom line is that certainly it's more likely to have discovered computers or the concept of computation than Coca-Cola, simply because computers seem to be. Certainly this suggests that there might be a way for aliens to have discovered computers independent of human beings. Okay, so the question is that are computers an answer to a question that occurs naturally to humans and aliens. So let's give some historical story behind this. And of course, the characters are Hilbert, Alan Turing. So Hilbert was a mathematician. We already know about Hilbert spaces, and he asked a question: what are the ultimate limits to mathematical knowledge? What parts of mathematics are forever unknowable to human beings? So, well, one can attempt to answer that question or attempt that question, recast it in form of algorithm. So the question can be, is there a general procedure or an algorithm a mathematician can follow uh, which would let them figure out whether any given mathematical statement is provable or not. So, as an example of an algorithm, let's say I have two numbers a, b. I have an algorithm and I multiply them, a, b. So I have an input, I have some procedure, and I have an output. So Hilbert's machine could have an input as a mathematical conjecture, an algorithm, and some sort of an answer, yes or no, whether it can be proved or not, it's true or not. So roughly that sort of is the recipe, and well, here enters Turing, Alan Turing, and he essentially put these things on a even more concrete way, and see, up to this point, even the notion of an algorithm is very vague. What exactly is an algorithm? Rather vague. So Turing was interested in questions trying to attack Hilbert's problem, and that forced Turing to make precise exactly what he meant by an algorithm. Turing, what does one mean by an algorithm? So to do this, Turing described what we now call a Turing machine, a single universal programmable computing device that Turing argued can compute any algorithms. So he came up with a single universal programmable computing device to perform any algorithm. So till now, even Turing's arguments are sort of very heuristic, but it's still, this is sort of a historical view, but it's still, it's good to see his thought process. Essentially, what he's saying is that algorithm is what could be performed by a Turing machine. Of course, it's a kind of an argument. Turing was arguing that a single fixed device could initiate any algorithmic process whatsoever, provided that the right program was supplied to it. So, what was his line of thought? Well, his line of thought was basically how to imitate an algorithmic process. Of course, the original Turing paper is a bit lengthy to read, but and his arguments are too long to produce here. But essentially, the sort of a machine he gave was a tape which had some symbols on it, a pointer, and he also had a state of a system. And some sort of a lookup instruction table which essentially took the current symbol and the state to determine the action of the pointer. And the pointer can erase, write, or shift left, right, so on and so forth. So, well, a computation starts and goes through a sequence till the halt state is reached. So it's quite interesting that the ideas what inspired him. If you go through his paper, he's actually kind of mimicking a child's arithmetic book. You know how well children deal with a math book which is two-dimensional, but he argued that these two-dimensional notebooks are not required. He replaced it by a one-dimensional notebook, and the state of the system is the state of mind of the child or the guy who's doing the calculations, and he's writing new symbols on the basis of the symbol, so on and so forth. Obviously, this is a sort of an informal and a heuristic argument, but it seemed convincing enough to argue that any algorithmic process essentially can be implemented or performed using this Turing machine. So, of course, the Turing machine is what our modern day computers are in some sense, and we've sold 1 billion of them. So, essentially, if there was such a device, you could perform any algorithm whatsoever, and this would be a truly universal. So Turing machine, which is a truly universal computer. That was Turing's thesis, and in some sense, let's just formally write down the statement. It says that computation is a process that can be implemented on a specific machine called the Turing machine. And sort of it makes sense, you know, an algorithm is a sequence of steps if you look at it, and the Turing machine seems to have the right kind of ingredients to follow systematically what an algorithm is doing. And the Church Turing thesis also says, Church is another scientist, by the way, that any physical computing device is at most as powerful. Any physical computing device is at most as powerful or I can even say efficient as the Turing machine. So one Turing machine is equivalent to another Turing machine, and any computing device you can make can be no powerful than the Turing machine or more efficient than the Turing machine. There might be some overhead, but fundamentally it's doing the same sort of a thing. So interesting. We also discussed, you know, one departure from a modern quantum mechanic could be that, look, I mean, all parts of the Turing machine, its symbol collection, the tape, everything is distinguishable. Whereas in quantum mechanically, things were not that distinguishable. And we'll see that. But essentially, so historically, Turing's ideas were, though heuristic, convincing enough for people to believe in them. Yet, still, there might be questions about what actually is an algorithm. As someone pointed out in the class, it still seems to be a slightly circular definition that an algorithm is something what a Turing machine implements. So, enter David Deutsch, the physicist who suggested a deeper approach to the problem. And Deutsch basically pointed out that every algorithm is carried out by a physical system, whether it be a paper and pencil, a mechanical system, some IC and circuits, something like that. So ultimately, all algorithms are a subset of all physical processes. So essentially, what Deutsch is getting at is that Deutsch's question is, David Deutsch, is there a single universal computing device which can efficiently simulate any other physical system? So certainly, if algorithms are a subset of all physical processes, then, well, then the Deutsch's universal computing device, indeed it's a truly universal computing device, because in the Turing sense, well, if it can simulate all physical processes, it seems like the algorithms are a subset of them. So this is the Deutsches device, Deutsches universal computing device. And the good part is that you don't need any informal heuristic Turing type argument to the notion of algorithm. So because Deutsch's argument hinges on the ability to simulate all of physics. So by making algorithms a subset of all the physical processes, don't need any informal heuristic Turing type of an argument. For these things, one could use the laws of physics to justify that the device is universal. Well, then of course you might ask the question, are algorithms a subset of physical processes? Well, my current thinking is yes, certainly yes. After all, informally, algorithms takes you, what's an algorithm? It takes you from one step to another step to another step, where each step has to be physical, and the process itself is physical. So, by the way, in a sense, we have to also remember that Deutsch was a quantum mechanic, and usually the experience, our experience tells us that simulating or performing quantum tasks on a classical computer is either are impossible or they can get very, very hard. The size of the Hilbert space, for example, for a system of 100 electrons with only spin degree of freedom, well, that might require a memory of this size, simply the dimension of the Hilbert space. So Deutsch posed this question that does there exist a device based upon quantum mechanics that would violate the Church-Turing thesis? So, by the Church-Turing thesis, of course, I mean this guy. Any physical computing device is as powerful as the Turing machine. So this is my Church Turing thesis again. Over here. Can there be devices based upon quantum mechanics which are more powerful than the Turing machine? Or can Turing machines be extended to get a notion of a Turing machine involving quantum processes? And as some students were arguing in the class, ultimately a quantum computer, so to speak, with inputs as quantum states, operators, outputs as quantum states. Indeed, that's an extension of the Turing machine, and the quest is to use quantum mechanics to argue that there can be devices more powerful or more efficient, certainly, than the Turing machine in back of the 1930s. So essentially, that was, therefore, the conclusion of this lecture is that, therefore, if the answer to Deutsch's question is yes, then we should start seriously thinking about a quantum computer. So this was sort of a lecture to motivate you enough that essentially these ideas, deep ideas about what actually is computation, what is the operational interpretation of quantum computation, operational interpretation of computation in terms of a machine or something concrete in this physical world, and does nature present us more richness or more resources that can be harnessed to make devices superior to Turing machines? Thank you.